in the universe. It was emitted 380,000 years after the Big Bang, when the universe was in a hot, dense, early state. And BICEP2 is designed to search for patterns of polarization in that light. So you see behind me such a pattern depicted as lines on the sky above the BICEP2 telescope, and that's the actual BICEP2 polarization map that's been projected up there. So in particular, BICEP2 is looking for swirling components to those patterns called B modes. So the theory of cosmic inflation, which attempts to explain the start of the Big Bang itself, predicts that the early universe will contain a background of gravitational waves that produce such a swirling B-mode pattern of polarization, particularly on angular scales of a few degrees on the sky. And today we're going to be reporting the detection of B-mode polarization as seen by the BICEP2 telescope that matches very closely the predicted pattern. Okay, so our team, which is shown in part here in this photograph, has just posted online scientific papers and all of our data products describing our observations. And before we go into details talking about those, let me introduce who the team is. So the four up here today are the co-leaders of the BICEP and Keck array series of experiments of which BICEP2 is a part. So I'd like to highlight contributions from other major collaborators that you see in BICEP2 over the past years, including UC San Diego, Brian Keating's group there, the Lionel Dubon's group from CEA in France, NASA's JPL, Ken Irwin's group at NIST, Peter Ade's group at Cardiff University, Bart Netterfield's group at the University of Toronto, and Mark Halpern at University of British Columbia. So those are all the senior people, but what we really should do is we should highlight how many young people in science have started their careers off by dedicating years of effort to making this project possible. So you see here depicted photographs of the BICEP2 postdocs and graduate students. These are the people who have dedicated their fellowships or their PhD theses, years of effort to making these projects work over the past 8 years. And also, a project like this doesn't happen without somebody volunteering to spend a 6-month-long night at the South Pole, the so-called winter over, who operates the telescope on his own at the South Pole for the 9 months of the year, actually, that it's inaccessible. And so for the BICEP2 project, the winter over in 2010 was Stefan Richter, and the winter over in 2011 was Stefan Richter. And the winter over in 2012 was Stefan Richter again. And Stefan is here in the audience. And he's still smiling. Amazing. Okay, so BICEP2 is the second telescope in this series, the BICEP and Keck array series of telescopes. So the first in this series, BICEP1, observed at the South Pole from 2006 to 2008. It was very successful, and it set the best previous limits on this B-mode pattern of polarization in the sky. So we parameterized the amplitude of that B-mode pattern in terms of the ratio of gravitational waves that it would produce compared to the ratio of regular fluctuations, density fluctuations in the universe. That ratio R was constrained by BICEP2's measurements to be less than around 0.7. Less than exactly 0.7, in fact, at 95% confidence. So BICEP2 picked up where BICEP1 left off, observing from 2010 to 2012 for 3 seasons at South Pole. New technology allows it to be 10 times faster than BICEP1. And we've already made BICEP2 obsolete. The Keck array started observations a couple years ago at South Pole. It's got essentially 5 BICEP2s observing on the sky at the same time, trained on the same patch. It's 5 times faster than BICEP2. And it will soon be joined at South Pole by BICEP3, the third in the BICEP series and 4th in this series of experiments. Okay, so what does our experimental strategy look like? Behind me you see the South Pole station itself. You see the living quarters, I believe it's on the left of the screen, and a runway where the planes land, running down the middle of the screen. And to the right you see all of our observatory buildings. And on those observatories we have our telescopes. They're all small aperture telescopes that are targeting this science goal. So these are not big dishes that we are using for our experiments. They're optimized to target the 2-degree scales on the sky, where the B-mode signal from inflation is expected to peak. And they integrate continuously from the South Pole. An extraordinary thing about the South Pole is that the sky rotates around a point above your head. So if you want to train your telescope on one patch of sky and collect photons from the CMB on that patch of sky for a long period of time, you can do it 24 hours a day, 365 days out of the year. You just have your telescope track that field around the sky, and you can see our telescope scanning back and forth on that small patch of sky and moving with it as it tracks around. So this is what the Keck Array telescope looked like last week, scanning at the South Pole. BICEP had a similar strategy here. We call this relentless observing. And this is what it looks like now before the sun goes down. But at the South Pole, once the long 6-month night begins, you get sometimes these really spectacularly beautiful skies above. So the thing that's dominating the brightness of this sky is the aurora. But you can see, and our telescope isn't affected by that, but you can see also rising almost vertically above our observatory building the plane of our own Milky Way galaxy. So when you ask, what is the small patch of sky that we train our telescope on? Well, what we try to do is we try to point as far away from that Milky Way galaxy as possible, because that Milky Way galaxy, in microwave emission, actually has a non-negligible contribution to the radiation, radio emission and dust emission in our galaxy. It can be polarized and can confuse these beam mode measurements. So we pick a patch of sky that is the so-called southern hole, the cleanest patch of sky that we can train our telescope on. And we observe that relentlessly for 3 years straight. So I'll hand it over to Xiaolin now.
So it's pretty interesting that I get the part that's already pretty well covered and explained in all the rumor weapons out there. So our general scientific strategy is to use the gravitational wave background that can travel across the entire history of the universe, and we use that to study the very first moment of the Big Bang. So you can't quite do it with just photons, because as John said, cosmic microwave background was the oldest light from the universe, but it's not old enough for us. It was already when the universe was 400,000 years old. We want to study the very first beginning of it. So you can think of cosmic microwave background. Before that, everything was ionized with charged particles, making it opaque to photons. So as a curtain of something, you can learn a lot from microwave background, but it also blocked the view, the very first beginning from us. So if you take gravitational wave instead, because the early hot, dense stage is still transparent to gravitational wave, you can use it to directly see what happens at the very first beginning. So in this picture, it shows it reveals the inflation process. So how do we do that? Gravitational wave leaves a very specific imprint, as John just said, of a swirly pattern on the polarization state of cosmic microwave background that we call B modes. And it looks like that on the screen, this swirly pattern. And by looking at that, the images of those swirly patterns, we are directly making images of gravitational waves created at the very first moment of Big Bang. So I would always thought of inflation as the bang of Big Bang. I'm not sure, what the big part is about, but so inflation was proposed in late 70s and early 80s to explain a series of classical problems in cosmology related to the expansion of the universe. I'll just give an example. Why was the universe created so uniformly? And the solution that inflation proposed was if the universe went through a rapid spatial expansion, like what's depicted here, then this superluminal placement of regions can set up the right initial condition to give us a uniform universe. This is a pretty hard concept, but I'll just leave it at that without going into great details. So there's one more amazing thing that inflation does. It's the generation of perturbations. So according to Heisenberg's uncertainty principle, there is big vacuum fluctuation even in empty space. So the field that was responsible for inflation, which we call inflaton, has that vacuum fluctuation. And the rapid expansion of inflation pretty much just amplified or stretched that initial 0-point fluctuation into density fluctuations studied by Planck, WMAP, SPT, ACT, and many other experiments. And those are the seed for structural formation. It creates, under gravitational instability, it creates galaxies, clusters, and so on. So it's a very important part. So today, we've detected the other half of inflation. So gravity, the zero-point energy of gravity, has fluctuation as well, we think. And inflation can, again, amplify that, stretch that, to make it a classical gravitational wave in the early universe. And that's exactly what we see with BICEP2 in the polarization of cosmic microwave background. So basically what we did today was to discover the other half of inflation, completing the picture, the paradigm of inflation. We verified the existence of a new field, a new particle, if you will, inflaton, and we set the energy scale at the grand unification scale. So that's what we did. So as John and others mentioned a few times, when this picture was proposed in late in 80s, people thought, there's no way to distinguish density perturbation from gravitational wave. But in 97, several clever theorists came up with a method. So they realized you can separate, and Mark Minkowski is one of the here with us, and he'll comment. So they realized if you linearly decompose the polarization state, polarization pattern on the sky into a mode called E mode, and a swirling pattern, B mode, and density perturbation, the mundane type of perturbation that we know of, can only generate E mode perturbation. And gravity wave can generate E mode and B mode. So if you see B mode, the only possibility on these angular scales at least is coming from a gravitational wave. So by imaging B mode, you're directly seeing images of gravitational waves in the CMB. So that's all very nice. So the pattern is very distinct. However, the signal is very small. Okay, so you're trying to measure the polarization. So you often do that by turning a polarizer 90 degrees. And the level of polarization that BICEP just reported corresponds to about 1 part in 30 million. That's different in power in vertical versus horizontal. So while this is a nice theoretical prediction, and the hunt was on since 97, it took us 17 years to get here. And we did so with modern technology that Jamie will describe.
Okay, thank you, Charlene. Now that Charlene's described what we're trying to detect, I'm going to say a few words about how we do it. So BICEP was invented in 2001 with a single goal in mind, and that was to make the deepest measurement technologically possible of an inflationary polarization signal in the microwave background. BICEP was really the first experiment of its kind, and it was based on a radical concept, which is to use a small telescope with just enough resolution to detect the polarization fluctuations where they're brightest at an angular scale of about 2 degrees. Now that small telescope is 2 lenses like a spyglass, and the primary aperture of our telescope is about 26 centimeters. But don't let its small size fool you. Our telescope has enormous light gathering capability. And so in fact, the field of view on the sky is 20 degrees across. And with a small telescope, we can do things that are simply impossible to do with a large telescope. So the first thing we do is we take our small telescope and we cool it to 4 degrees above absolute zero. And then we surround the telescope with absorbing material, which soaks up any stray radiation. That's very difficult to do with a large telescope, of course. Furthermore, with a small telescope, we can pick up the whole telescope and spin it around its axis to remove any polarization properties that might be associated with the instrument itself. The optics of this instrument, as I mentioned, are these 2 lenses, but they're designed to have a focal plane that's flat, which meant that when the best technologies came along, which we were developing back in 2001, they would just pop right into the focal plane, and in fact, that is what happened. And finally, in order to achieve the sensitivities we need, the focal planes cooled down to just 0.25 degrees above absolute zero. Okay, on the left is showing what a state-of-the-art focal plane would look like in 2005, and that's the BICEP2 focal plane. It has about 100 detectors, and that was state-of-the-art at the time. The detectors in this telescope are actually limited to a large extent by photon noise from the background it observes, and in fact, we can build detectors that are limited by photon noise from the microwave background itself in space. So the name of the game is to build more detectors, and it's a challenge that might be similar to taking what was film in an analog camera and making an array detector out of a CCD chip. But in fact, the problem is actually much more difficult. The focal plane on the left is not just like the film in the camera, it's like the camera. The focal plane actually gathers the light, chooses the wavelengths that are observed, it analyzes the polarization, it detects the radiation, and it amplifies the signal. And so the question is, how could we mass produce such a technology? And so the focal plane that you see on the right basically is an approach of building that camera on a printed circuit board so that it can be mass produced. The BICEP2 focal plane on the right has 512 detectors, and as a combination of the detectors being somewhat better and having more detectors, it makes observations 10 times more quickly than BICEP1. So an observation, the data we have with 3 years of BICEP2 would have taken 30 years to obtain with BICEP1, and while I love the poll, another point here is that these approaches are actually quite different. And in our results, we compare the results of the two experiments, and they agree, which means that the properties of the instrument are well controlled. So how do you make a camera that detects polarization at 250 millikelvin on a chip? The answer is to use superconductivity. And briefly, our approach is the lens of the camera is replaced by what is essentially a circuit board printed antenna. The antenna gathers the light, chooses the spectral band, and that light from the antenna is passed to a detector. And this process is all built by photolithography, so it can be mass produced. This is the sensing element at the end of the detector, and at the end of the antenna. And basically what happens is that microwave background light propagates through the antenna to a suspended island of material, thermally isolated by tiny threads of a film. And the power from the microwave background is dissipated, it's turned into heat, into that meandered resistor. And that heat is then sensed by a superconducting thermometer bias just on its transition between normal and superconducting state, and read out with a series of superconducting amplifiers developed in NIST. This map just shows our observational data as time goes on. Here, this movie. And what you see on the left are our signals. It's decomposed into two polarization states. So as time goes down, time goes on, the signal becomes more and more apparent. And the right is showing a difference map, which should be consistent with 0. And one can see the noise getting smaller and smaller and smaller. I should say that the noise in our maps, we achieve a sensitivity below 100 nanokelvin in a degree, a square degree of sky. That's 100 billionths of a degree Kelvin on top of the 2.7 Kelvin CMB signal, with a total combined sensitivity of about 3 nanokelvin. The pattern you see in these two polarization signal maps, you can see on the top figure it sort of has a vertical horizontal pattern, and the bottom map looks kind of like chicken wire with a cross pattern. And those patterns are characteristic of our signal being dominated by the E-mode polarization pattern that Xiaolin mentioned. But lurking beneath that is a B mode signal.
Okay, so this is the actual polarization pattern map as measured by the BICEP2 telescope. So this is the total polarization signal. It's basically the previous map turned into little, call them pseudo-vectors, little lines, illustrating the direction at which the polarization is oriented from different points on the sky. So the x-axis is one direction on the sky, the y-axis is the other direction on the sky. It's a map, a polarization map of the sky. The most sensitive polarization map ever made at these angular scales. You can see there the scale at the top is showing you how long, so a long line on this plot is 1.7 microkelvin, 1.7 millionths of a Kelvin. And so that's the raw map that we've measured. And you can see that it mostly has a kind of, well, it mostly has a non-swirly pattern, right? If you look at where the lines are big and where they're small, and then you look at the direction of the lines moving from a region where they're big to small, the lines are either parallel or perpendicular or at 90 degrees to that direction. So this is the E-mode pattern. This raw polarization pattern is dominated by the so-called E-mode pattern. And that E-mode polarization a few years ago was fantastically hard to measure and fascinating scientifically. But now it's just getting in the way of measuring the thing that we're really after, which is the B-mode. So times change very rapidly in this field. So taking that pattern and subtracting away the E-mode, we do this. Okay, so we mathematically operate on the map to remove the E-mode pattern, the part of the pattern that we're not interested in, and that leaves behind the B-mode, so the swirly part of the pattern that we are interested in. And you can see that that's a very small fraction. So this is a very difficult experiment to do because we need to achieve very high fidelity, not just very high sensitivity, as Jamie has just emphasized, but very high fidelity. If each of those little polarization vectors was twisted by even a few degrees away from the true direction, then the amount of B mode, the amount of swirliness in there would either be exaggerated or possibly cancelled out. So it's fantastically important that we achieve very high fidelity. So we have labored long and hard. We've been working on this data analysis for about 3 years straight, a large team of people, as John emphasized, trying to do all possible cross-checks and data slicings that can convince us that we really understand every aspect of the instrument sufficiently well, and that there really is no false polarization that's being introduced there, or any kind of distortion of the pattern that would induce a false B mode. So we're firmly convinced now that the B mode that's left when we remove the E mode is truly there. It's truly on the sky, as we like to say, which means it's out there coming to us from the universe, right, rather than being induced in the instrument or maybe by contaminating emission from the ground. So let's flip the scale. So going from this slide to this slide, all we're doing is we're just amplifying the scale. So the scale is going from 1.7 microkelvin for a full-length vector to being 0.3 microkelvin for a full-length vector. So basically like a scale of a factor 6. So you can see that when we do that, the swirliness of the pattern is thrown into stark relief. We can see that indeed this is the swirly pattern that we're after. And what we've done is very carefully shown that this pattern is in excess of noise. It's not coming from the instrument. It's really coming from the sky. So then the question is, what is it? And we've done many further studies to try and convince ourselves that it's not foreground emission from our galaxy, because our galaxy also emits at these wavelengths very, very weakly, but the signal that we're after is so weak that it could potentially still be a problem. So we are convinced on the basis of all the studies that we've done that the signal is real. It's coming from the sky, and it's coming actually from the microwave background itself, from that 400,000 years after the beginning point. As Sheldon emphasized, by far the most reasonable interpretation of such a signal is that it is gravity waves written in that last scattering surface pattern, in that microwave background pattern, and those gravity waves come from the inflationary epoch at a tiny, tiny fraction of a second after the beginning. There's one final slide here where we add color to it. The color is really the B mode itself. And you can see that if you look at the vector pattern around, for instance, a hot spot, a red spot,
we have an anti-clockwise circulation pattern, and around a cold spot, a blue spot, we have a clockwise circulation pattern. So that's exactly the pattern that we're looking for. Now these following two plots are a little hard to explain to a non-specialist audience. The multipole number is angular scale, going from large angular scales at low multipoles to high angular scales as we move to the right on the axis. The angular scales that we're most interested in are about 80, and that corresponds to an angular size of about 2 degrees on the sky, which is about 4 times the diameter of the full moon. The data points are the actual measured data points, and here we have data points from BICEP2 alone, the first set of points, and then also BICEP2 in cross-correlation with BICEP1 and in cross-correlation with the Keck array, the third generation experiment that John mentioned. The colored lines, the red lines, are the theoretical expectations. The lower one, where it says B mode from lensing, that's the theoretical expectation if there is no gravity wave signal. And then the dashed line adds in the theoretical expectation from a gravity wave signal. And so you can see that the data points basically sit on the dashed line. And so this is a very high confidence detection of an excess in just the place where we expect it, if in fact there are these gravitational waves from inflation. So this final plot is the same data plotted again, but now on a logarithmic scale. I'm not going to go into too much what that is, a kind of powers of 10 scale. And you can see the data points from previous experiments as the massive colored points. And those were upper limits. They were setting limits that, okay, if there is a gravity wave signal, it has to be smaller than the position of the point in a downward direction. But now, finally, with these BICEP2 results, we have for the first time an actual detection of the mythical gravity wave signal that people have been searching for so long, so hard for so long. Now, we may be the first, but there are many experiments coming down the line, many competitors out there. They've actually mostly been focusing so far on measuring the B mode from lensing at those smaller angular scales, those higher multipole numbers. But they will certainly soon be confirming our results, we hope. So there's many more experiments coming, SPT-pol, ACPOL, EBEX, Piper, I don't know, I'm not going to get them all, I'm sorry, there's quite a number. Okay, so that is our conclusion, and turn it over to Mark and tell you what to think about it.
It's not every day that you wake up and learn something completely new about what happened 1 trillionth of a trillionth of a trillionth of a second after the Big Bang. And I don't think that you need to be a professional cosmologist to think that's really cool. So just to clarify, I'm not a member of the collaboration, as you can tell, because I'm not wearing one of these nifty t-shirts, which they sell only at the South Pole. Inflation has for some time been something to be taken quite seriously, especially after the transformative results that we've seen from the cosmic microwave background measurements the past decade and a half, and in which, for example, Jamie played a particularly important role. The issue, though, is that inflation requires some new physics beyond the 4 fundamental forces that we know about. So over the years, theorists have developed a ton of ideas as to what this new physics might be, but until now we've had no way to discriminate between these different ideas. This gravitational wave signal that they've detected, though, can help us out. The strength of the signal depends on how energetic inflation was. Inflation models span a huge range of energies, and so a precise measurement of the energy very dramatically narrows the range of inflationary models. In particular, this measurement suggests that inflation may have had something to do with unification of the strong, weak, and electromagnetic forces, ideas that particle theorists have been entertaining since the 1970s. So, this detection is cosmology's missing link. It's something that we thought should be there, but we weren't really sure, and it has been eagerly Hadron Collider at CERN. Since these gravitational waves are produced by a Hawking-like process in the early universe, we're seeing Hawking radiation here. And this is also the first detection of gravitational waves, a consequence of Einstein's general relativity, which next year will be 100 years old. Of course, as Carl Sagan said, extraordinary results require extraordinary scrutiny. And these results are as extraordinary as they get, and they will require the most extraordinary scrutiny measurements to infer fully what this telegram is telling us.
I want to begin by thanking our presenters for taking a very complex subject and making it more understandable. There has been tremendous interest in this out in the wider community. In fact, I'm told that we brought Harvard servers to their knees with the webcast of these things. Not to worry, it will be archived online afterwards. So at this time, we are going to take questions from the media. We will begin with the media who are in the room here and then move on to email questions. I want to ask that you state your name and affiliation and wait for the microphone. So do we have any questions from the media in the room? Yes. Courtney?
Scrutinize this with different kinds of skepticism. And so the cross-spectrum that you mentioned at the collaboration meeting here last year was with the Keck array data. And as the process evolved over the past 12 months, last fall particularly, we set for ourselves, because, as Clem says, the story that we're testing here with this data set seems so fantastical. We know it's good physics, but the extrapolation from the physics that we understand combined with these models that have been built by theorists to testable predictions that come from such an incredibly exotic regime at the beginning of our universe. We need a lot of convincing to believe that the signal was real. And the emotional process for us was helped by setting a series of concrete tests, milestones that data needed to pass through the end of last year. And by last December, the data was passing each of those tests.
Frankly, if we didn't have this program of 3 very different experiments where we could cross-compare, I think we'd still be scratching our heads.
Do we have any other online questions?
This question is from Miriam Kramer from space.com. Could someone please expand on why more evidence for inflation also hints at the idea of a multiverse? And the question to Dr. Good.
To me?
To Dr. Good? Yes. Okay. Look at that microphone over there.
Okay. I'm sure Andre will want to weigh in on this also, so I'll give an answer and then I'll hand the microphone to Andre. But basically, the point is that inflation depends on essentially a kind of material that turns gravity on its head and causes it to be repulsive. We describe this material in terms of usually a scalar field. And in order for inflation to work, this metastable state of the scalar field in a peculiar position has to be stable enough to survive during the period of inflation itself, which requires about 100 doubling times or so of the size of the universe. The process by which inflation ends is very similar to the way radioactive decay works. It's a probabilistic process. There's a half-life. And the point is that for inflation to work at all, the half-life of this metastable material has to be long compared to the doubling time of the exponential expansion itself. So in a nutshell, if you wait for a half-life of the decay of the material that's driving the exponential expansion, during that time, half of this peculiar material will decay and become normal material. But in the meantime, the volume of space would have increased by a much larger factor. So the total volume of the region that's inflating tends to just increase uniformly in time. And that's the simple picture, and one has to go to odd extremes, really, to avoid that picture.
And if I may add something, is that, well, just think about some unstable state. You are staying on the top of the hill, and then you can fall in this direction, you can fall in another direction, and if you're drunk, eventually you must fall. So, inflation is exponential instability of our space with respect to its expansion. So you have something growing exponentially. If you just let it go, if it does not go to the minimum, it will continue exponentially growing. So this is like one possibility of something going wrong, this instability, except for it's very, very right for us. So if, because it creates all space, and now we know that if anything can go wrong, it will go wrong once, and the second time, and the third time, up to infinity, as long as it can go. But at least we did have this experience back in Russia. So wondering, and now this brings us naturally to the idea of the universe when one part of it starts expanding and then it stops, so it becomes right. But there are some other parts where things go wrong and they continue expanding, and they produce some other parts where everything is normal, like around us. But the remaining continue go wrong, continue expanding, growing wrong. This process must go on forever. Thank you.
We're running low on time, but we have one more question online.
This question is from Irene Klotz from Discovery News. What is the significance that the signal was twice what was predicted?
Okay, yeah. So maybe we should clear up some confusion. I don't know that the signal that that's favored by our data, the amplitude of the B-mode signal that we see, is twice what was predicted. The question probably refers to the fact that the interpretation of the existing data from the temperature of the CMB combined with the simplest model that we have of the early universe, I should say the standard model, lambda CDM, folding all that together implied a constraint on the expected level of the gravitational waves that was lower than the value that's favored by our data. But it's a very different kind of constraint. It's a very model-dependent kind of constraint in the sense that that's looking at statistical power on the largest scales in the temperature variations that we see in the microwave sky, and saying there seems to be too little of it already, not enough room in the power that we observe to add in an additional contribution that you would expect if there were gravitational waves. But it's a statistical argument, and it depends on model-dependent extrapolations down to those scales. So there could be many ways of resolving the differences apparent in that indirect constraint and the data that we're presenting today, which appears to directly show the signature of these gravitational waves at a certain amplitude.
There's also a considerable degree of uncertainty on the amplitude that we've measured, because we've only measured a small patch of sky. So we have very, very high sensitivity, but we only have a relatively small sample of sky. So there's, a value half as big as our most likely value is not that unlikely. Right? So a value of 0 is extremely unlikely, but a value half as big as our maximum likelihood value is not that unlikely. So it may be that the tension is just a statistical fluke, and really will just go away.
However, it is very interesting to follow it up. If we follow up and we tighten the error bar and it clusters around 0.3, then it makes it extremely interesting, because that tension will now be inconceivable, basically.
With that, I would like to conclude our news conference. I want to thank all of our presenters again, and thank all of you for joining us for this historic announcement. Have a